next speaker is Badih Assaf. He's going to talk about altermagnetic alpha manganese tellurium thin films grown by molecular beam epitaxy.
Okay, is my audio okay? Everybody can hear okay?
Yes.
Okay, so I realize that I'm the last one, keeping you from going to dinner. So I'll keep this to 20, 25 minutes. And this talk is experimental, and it's gonna cover some of our findings on measurements from manganese telluride thin films grown by MBE. I'm from the University of Notre Dame, and before I start, I should probably thank the organizers for including me in this workshop, but also for accommodating the time zone difference. This is pretty convenient, so thank you for making that happen. Um, so this talk actually involves a lot of people, but I should thank maybe four of them more than others. So Sarah Bay has done a lot of the measurements. She's a grad student in my group. Xin Liu has grown these materials by molecular beam epitaxy. And I should also acknowledge Shelby Fields and Stephen Bennett from the Naval Research Lab, who have been supporting us at different levels to do, low temperature XRD, some fab, as well as some measurements. And this is supported by National Science Foundation for Growth and Structure, and some of the anomalous Hall effect is supported by DOE, some of those measurements. So you've heard this introduction many times, so I actually won't go into it in as much details. But as you've seen in the previous talks, I can safely say that we now have a new magnetic state of matter called an altermagnet, which is not a ferromagnet, meaning that it doesn't have a spontaneous magnetization as its primary order parameter, which leads to exchange splitting of your band structure. It's not a simple antiferromagnet in the sense that even though it can be described by an AL vector, in real space, which essentially is the difference between the magnetic moments of two sublattices of an antiferromagnet. It's not as simple as the antiferromagnet in momentum space, where in the antiferromagnet you just have essentially no spin splitting. It's a state where the Néel vector remains one of the order parameters. That's why I'm putting it in quotation marks. And I'm going to use it later on, but it's a state where the real space picture, the low symmetry of the crystal in the low space picture, allows and gives rise to spin splitting in momentum space. And this spin splitting causes a lot of the electrical and optical features that you normally see in a ferromagnet, despite the fact that these materials have zero and almost vanishing magnetization. And this is something that I'll show you experimentally in a bit. So experimentalists like myself are getting interested in this because there are predictions that an altermagnet in a way can behave like like a ferromagnet when you make magnetic tunnel junctions out of it. You can create what we call GMR and TMR effects. I won't go into this, but several papers have explored this, and I'm citing a couple of them here. I know you can. The bottom line is that you can actually make these devices. You can read out the data and maybe manipulate it, but you can read it out of bits that do not have a spontaneous magnetization, and so do not have a stray field. So according to that logic, you can make denser and denser memory devices. So essentially, altermagnets marry both aspects, both advantages of ferromagnets and antiferromagnets. They don't yield stray fields, just like antiferromagnets don't. They also have the terahertz manipulation speeds expected for antiferromagnets. And they overcome a big difficulty that people have faced in the field of antiferromagnetic spintronics, and that's the difficult aspect of measuring the order parameter of antiferromagnets. So this is why a lot of us have really gotten interested in this field, and this is why growers like myself have started making these materials. Now, maybe the prototypical material to study, and the one that's probably the most interesting from a fundamental point of view, is manganese telluride. I'm showing its crystal structure here. It has in its alpha phase, it has this hexagonal structure where the in-plane magnetization points along the 1 bar 0 0 direction, and it's ferromagnetic within one layer. But then the interlayer coupling is antiferromagnetic and leads to a vanishingly small magnetization. Now, you cannot map one sublattice to the other using inversion or translation. So there are symmetry arguments that are accepted now that make this material an altermagnet. Now, what's also interesting is that its Néel temperature is very close, but slightly higher to room temperature. So you can actually tune in and out of the antiferromagnetic state. without needing to heat up too much. And this material turns out to be a p-type semiconductor. So a lot of the electrical manipulations that we've learned from the field of magnetic semiconductor over the last couple of decades, as well as topological phases of matter, apply here. You can dope this material, potentially, you can gate it, even though that hasn't been done yet. And the analysis of the symmetry of this material has also revealed that the anomalous Hall effect is allowed in it as long as the magnetic easy axis is along this 1, 1 bar, 0, 0 direction. All of this happens, so this intrinsic anomalous Hall happens despite the fact that the magnetization is tiny in this material. This is an actual measurement. And you can see that below what we call the spin flop field, essentially at zero magnetic field, the magnetic moment is vanishingly small. We cannot even detect it by squid magnetometry. We can put an upper bound on it that's on the order of 10 to the minus 3 Bohr magnetons per manganese, but it's really an upper bound. It's not a measurement. Despite this, there are people reporting, there's already papers reporting the anomalous Hall effect in this material, including ours. In single crystals, this was seen as early as 1965. But in thin films, it really came into light more recently. By the way, the single crystal result has been reproduced recently in 2024 by Kluchik and co-authors. But in thin films, most of what's reported is grown on indium phosphide, and as I'm going to show later, this synthesis on 3,5 substrates is actually a little bit subtle to understand because of the strains that are introduced by these films. So the bottom line that I will show in the slide is that, there's been decent measurements on this material done in single crystals, but ultimately you need thin films to make devices. And if you want to make films, you really have to understand their strain, their topography, what happens when you put your material on an interface to really understand what's going on in an altermagnet. So to an MBE grower, really films allow two levels of studies: controls, which include strain, nanostructuring, and doping under, and then interfaces, which are essentially the things that are going to lead to new physics in this field, like when you combine altermagnets with superconductors, with ferromagnets, or with topological states. And what I'm going to show you in this talk is some of the controls that we've already done on manganese telluride. So there are two parts in this talk. In the first part, I'm going to show you what I call the pristine anomalous Hall effect of manganese telluride films, which we observe when we grow this material on strontium difluoride, which turns out to be the substrate that has the best lattice match and the best compromise for lattice match and the best thermal expansion coefficient match. It turns out to be important. And then we grew MnTe on gallium arsenide as well, and there we observed a very interesting tunable anomalous Hall effect that we don't understand the origin of, actually. But we correlate its presence to thermal strain and stacking faults. That's what I'm going to show you in a bit. So let's start with MnTe on strontium fluoride. So our samples are grown by MBE. This is a picture of our chamber, slightly more low res than expected, but you can see the chalcogenide chamber hooked up to our vacuum tunnel. The films are grown by Xin Liu in this setup. And one aspect that's important to control here for manganese telluride is the crystalline phase that it nucleates under. So gamma MnTe, zinc blende MnTe, has been studied extensively in the past, and you want to tune your growth parameters to actually avoid nucleating this phase and and preferentially nucleate the alpha MnTe phase. There's tricks to do it on each substrate, but it turns out that on strontium difluoride, alpha MnTe is more favorable and just grows, for a very wide growth parameter window. What I'm showing here is X-ray diffraction patterns taken on films grown on both substrates, just to prove to you that we can control this aspect and that our films actually only exhibit this peak right here, this Bragg peak right there for gallium arsenide and right here for strontium fluoride that corresponds closely to the alpha MnTe peak. And we don't have any signal at all on a log scale for the gamma MnTe phase. Now, the reason why we choose strontium fluoride is because of the following. Notice that the thermal expansion coefficient of manganese telluride is quite high. It's about 1.6 10 to the minus 5 inverse Kelvin. That's at room temperature. And if you compare it to the thermal expansion coefficients of common 3,5 semiconductors, it turns out to be significantly higher. So it's not surprising that when you grow it on indium phosphide and gallium arsenide, that thermal strains are going to play a big role in dictating your properties. Strontium fluoride, on the other hand, also has a large thermal expansion coefficient. So it eliminates this thermal strain, essentially. Now, strontium difluoride has a slightly worse lattice match than indium phosphide, but turns out to be good enough to grow very good quality films. And in fact, when you grow thick enough, for the X-ray diffraction pattern that I'm showing here, the film is 100 nanometers, and you can see that it's relaxed. The Bragg peak that we see lies right on top of the expected Bragg angle computed using the bulk lattice parameters. So I'm calling these the pristine samples in a way. Now we go on and we measure the anomalous Hall effect. We can pattern Hall bars, stick contacts on them, and then you apply a current along this direction, field perpendicular out of the page, and then you measure the transverse Hall resistance. Naively speaking, what you expect from the Hall resistivity is for it to scale proportionally with magnetization. At least that's the picture for conventional collinear ferromagnets. And the perfect example to show here is a material that many of us in the community have studied, gallium manganese arsenide with phosphorus, where the anomalous Hall effect has this hysteresis shape that you can see here at low temperature, and qualitatively it's identical to the magnetization hysteresis. Now, manganese telluride turns out to be very different. You stick electrodes on manganese telluride, you measure it, you see this very strong linear Hall because MnTe is a semiconductor with a relatively low carrier density. You subtract the slope from this, and then you recover an anomalous Hall effect, allowed by symmetry. But what's surprising is that in that same sample, you go and you measure magnetization, and you see this plot that I'm showing you here. So in the out-of-plane direction, the magnetization is nearly flat after we subtract the substrate diamagnetism, essentially. And then if I orient my field in plane along the easy axis, again, I see something flat at low field, and then at about 1 Tesla, 0.8 Tesla, the magnetization starts to ramp up. In antiferromagnets, that's what's referred to as the spin flop field right here. And this rise is linear and doesn't exhibit any hysteresis when you sweep back down. Notice one more thing here. The values of magnetization are something like an order of magnitude to a factor of 50 smaller than what we see on gallium manganese arsenide. The spontaneous value of magnetization is almost absent in manganese telluride. It's at least 2 or 3 orders of magnitude lower than gallium manganese arsenide phosphide. But notice that the anomalous Hall effect has qualitatively a similarity between the two. And then the value of the anomalous Hall effect is about 0.8 milliohm centimeters at 5 Kelvin, which is something like a factor of 2 or 3 smaller than in gallium manganese arsenide phosphide. So the bottom line is that this vanishing magnetization generates an anomalous Hall effect that's almost on the same order of magnitude as magnetic semiconductors. That's kind of the fascinating aspect of altermagnets to me. We wanted to be sure that this is intrinsic, so we took this a step further. We did a thickness dependence. And it turns out when you change the thickness of manganese telluride, its longitudinal conductivity changes because its carrier density changes a little bit. And what that allowed us to do is to actually study the scaling of the anomalous Hall effect. So here I'm showing anomalous Hall resistivity, and longitudinal resistivity. But from these quantities, you can actually extract the conductivity, sigma xx and sigma xy, and you can plot the scaling relation between the two. That tells you something about the origin of this anomalous Hall effect. So our samples are black and green, and then we overlaid some of the literature on bulk in this plot and some of the other films grown in indium phosphide. And then the data falls very well on this line, which on a log scale, this is a log scale and that's a log scale, gives us a scaling law that's a power law to the sigma xy equal to sigma xx to the 1.5 almost. This is consistent with the hopping regime for the anomalous Hall effect, which was actually studied pretty well in magnetic semiconductors in the past. It makes sense in this case for it to be in this regime simply because manganese telluride is a semiconductor with quite a low carrier density, giving a relatively low sigma xx, a relatively low longitudinal conductivity. So this is not a surprising finding, but it hadn't been observed to this point, so it's important to highlight it. But what's more important is that these films on strontium fluoride fall on the same line as bulk. So we're calling their anomalous Hall effect the pristine anomalous Hall effect of MnTe because it occurs in a phase of the crystal that's unaffected by strain, that has the same lattice parameters as bulk, essentially. And what I'm going to show you next is that this is not quite the case for some of the films that have been studied so far, including ours, and that are grown on 3,5 substrates. That's what we've done beyond this study. We've studied heteroepitaxial manganese telluride grown on gallium arsenide. And there, we've seen a specific type of stacking fault and a specific type of strain whose appearance correlates with a surprising anomalous Hall effect. So let me start with some information about the strain state of MnTe on gallium arsenide. This is a reciprocal space map taken on the 112 bar 6 peak of manganese telluride. So you can think about the x-axis as, Qx is inversely proportional to the in-plane lattice parameter, and the z-axis Qz as something inversely proportional to the C lattice parameter of MnTe. For bulk MnTe, you expect the Bragg peak to be right here where that white point is, but then we see the Bragg peak to be offset from that point. If you extract the experimental A and C lattice parameters, you find an experimental A lattice parameter that's actually larger than what you expect for bulk. This was a bit surprising because the A lattice parameter of gallium arsenide 111 is actually smaller than bulk. So that tells us that the dominant strain source is actually not lattice strain. What it turned out to be is, this strain that actually stretches out MnTe in the plane turned out to be simply related to the fact that gallium arsenide has a very low thermal expansion coefficient. So when you cool down your sample from the growth temperature to room temperature, your substrate shrinks at a rate that's actually much slower than your layer, leaving your layer under tensile strain. It actually expands the in-plane lattice parameter. So bottom line here is that the C and the A values for the lattice parameters of MnTe grown on 3,5 substrates is actually very different from what's considered in most theoretical studies and most DFT calculations on this material. We can repeat this experiment down to 100 Kelvin. Measurements done at the Naval Research Lab with Steve Bennett and Shelby Fields and Nick Combs actually, and we can extract the C over A ratio down to 100 Kelvin. Turns out to be something lower than 1.59, whereas in bulk the C over A ratio is 1.61, 1.62 approximately. Now, there are there are band structure calculations that have actually computed how the strain or how this changing C over A ratio changes the electronic structure. And what these calculations have shown is that by reducing the C over A ratio, the Fermi surface moves from, or the band edge, the valence band edge moves from being at the A point of the Brillouin zone to somewhere close to the gamma point of the Brillouin zone. It's not known, however, if the magnetic easy axis is altered or if the anomalous Hall effect, the anomalous Hall conductivity computed from Berry curvature is altered in any way. These are still open questions. What we also find is that MnTe grown on gallium arsenide has a very peculiar type of defect. In TM, there were regions where we find that the periodicity of the lattice is interrupted. There's a zoom in on these shown here, where you can see that this zigzag pattern or this tilted pattern appears down here in the pristine region, and then all of a sudden there's a layer that appears a little bit more stacked vertically. The two tellurons are stacked vertically on top of each other right here. If you zoom in and study this carefully, it turns out that there's a stacking fault that happens along these layers, and there's a missing tellurium atom. You can see that right here, that there are two red dots corresponding to manganese right next to each other. It's also not known how the local moment is affected by these stacking faults. If this creates an unexpected canting or some MZ components that are actually not expected in the pristine structure. So we want to understand the anomalous Hall effect in the presence of these stacking faults and this thermal strain. We actually measured it in a slightly unconventional way. Instead of simply measuring, simply sticking wires onto your sample and measuring it, we did that, but we also figured out a training sequence. And we tested that training sequence where we cooled down the thin film, the manganese telluride thin films that we have under a magnetic field before we measure them. And we can apply a field along the easy axis, along 11 bar 00. We warm up to the nail temperature, and then we cool down under 1 Tesla or more or less sometimes, all the way down to 2 Kelvin. And then we shut off the field, we saturate with B applied along the C-axis, and then we measure. And we can repeat the sequence for a field cooling that's in the plane, either along Y, along the easy axis, 1, 1 bar 0, 0, or along the hard, one of the hard axes, the X direction, 1, 1, 2 bar 0. What we find is pretty impressive, actually. Without field cooling, our anomalous Hall resistivity looks like this purple curve that I'm showing here. So essentially, there's nothing. And then as you ramp up this field cooling magnetic field, you start to open a hysteresis loop, and the hysteresis loop grows bigger and bigger until you consistently get something that looks like a minor loop for fields as large as 6 or 7 Tesla sometimes. The highlight here is that a field as small as 0.03 Tesla allowed us to open a loop, and that the polarity of the field cooling is interesting. That the direction of the loop was actually odd under the direction of field cooling. So I'm going to reiterate this and show you a few more extensive measurements before I conclude. Essentially, when we grow MnT on gallium arsenide, we find that there's almost no anomalous Hall effect without field cooling. This is these two data sets shown here. And then if we field cool along X or along Y, we start open a loop and we start to observe a spontaneous anomalous Hall effect, whose quantitative details actually depend quite sensitively on the, on how you apply your magnetic field and also on its strength. And it turns out these details are also vary sample to sample quite a bit. Conversely, when we have MnT grown on strontium fluoride, the data set that I showed you earlier, the field cooling doesn't have an impact. Even if we don't field cool, even if we cool down under zero magnetic field, we do observe a spontaneous anomalous Hall effect. And then field cooling does not impact the quantitative details of this anomalous Hall effect significantly. So this anomalous Hall effect is unique to MnT grown on gallium arsenide. And we believe it's related to the properties of those films. So even though we don't have a full picture and an understanding of what's going on, we have a couple of hypotheses to explain it. So since in altermagnets, and specifically in MnTe, the anomalous Hall effect appears only for a specific orientation of the Néel vector, we believe that the lower C over A ratio is actually favoring a magnetic anisotropy that forbids the anomalous Hall effect. In MnTe, the anomalous Hall effect is only allowed if the easy axis is along 1, 1 bar 0, this Y direction. But if it's along the X direction, it vanishes. So it's possible that the strain is actually favoring this direction, and then by field cooling, we retrain the material to orient its easy axis along the Y direction. Field cooling will essentially change the Zeeman energy in your free energy landscape and could stabilize one anisotropy versus the other. Another hypothesis is that stacking faults actually alter the manganese-manganese coupling locally. As a result, there's an interplay between the local moment of these stacking faults generate and altermagnetism to tune the anomalous Hall effect. And on one hand, having it vanish without field cooling, and then on the other hand, allow field cooling to train some of these local moments that are localized around this defect to spontaneously organize and generate an anomalous Hall effect. I want to highlight here that the density of these stacking faults is still really low to account for the strength of the anomalous Hall effect, and that magnetometry on manganese telluride grown on gallium arsenide was still yielding moments that are on the same order of magnitude as I showed you earlier, 10 to the minus 2 to 10 to the minus 3 Bohr magnetons. So this is essentially my talk. I should be more or less on time. I've showed you that when you grow manganese telluride by MBE on various substrates, the behavior of its anomalous Hall effect is very sensitive on the details of its structural properties. When you grow it on strontium fluoride, which I believe is the ideal substrate to grow it on, we end up with an anomalous Hall effect that's as predicted, and that follows the scaling law expected for non-metallic materials. On the other hand, when we grow it on gallium arsenide and when we subject it to thermal strain, and when it actually hosts defects that are likely a result of the lattice mismatch on the substrate, we get this interesting and yet tunable and and very versatile anomalous Hall effect that requires something like 0.03 Tesla to appear, but that without field cooling seems to vanish. So the structural and electrical measurements on this study that we've done are actually in these two papers. They're already either posted or accepted in the literature, and this is still in preparation, but should come out recently. So this is it for my talk. I'll leave you this conclusion slide, and I can take questions at this point.
Okay, thank you very much. Questions? Jerome?
Thank you, Badih, for a nice talk. I was wondering, you looked at the directions 1, 1, -2, and 1, -1, 0, right? For the MnTe on gallium arsenide.
Yes, yeah.
So from the theory, should in both cases an anomalous Hall effect be present for those high symmetry directions, or is it in only one of those?
So let me reiterate something here. What we've looked at is field cooling along these directions. But I don't know for sure. I don't know, and it's not easy to actually figure out if the Néel vector is oriented in along 1, 1, 2 bar 0 or 1, 1 bar 0, 0. The anomalous Hall effect is only allowed if the Néel vector is along 1, 1 bar 0, 0.
Okay.
It's forbidden if it's along this direction. With magnetometry, it's difficult to actually probe whether it actually lines up with it in this case and doesn't with that case. So we kind of have to do something involving neutron diffraction to answer this question. But yeah.
Yeah. So
yeah,
the hypothesis
it's only allowed
is
in this
that it locks in. Yeah. Okay. It locks into 1, -1, 0, 0 upon field cooling.
Yeah, essentially that's one hypothesis, that it actually locks into this direction no matter which direction you field cool it in. And there's a reason why it might do that.
Right.
More questions?
Yeah, just wanted to ask whether you tried to make a really single layer, like in iron selenium, for example. Are you working in this direction or not?
Single layer manganese telluride?
Yeah.
So single layer is pretty tricky to make for transport because there's still a finite roughness. So these materials aren't perfectly flat. If you look at the surface, there's some roughness that's on the order of 2 to 4 unit cells. So if I make a single layer, it's very likely that there are regions that are bilayer, there are regions that are, maybe 3 layers even. So that's very tricky, and it's not one of our priorities right now. But there are probably experts in STM that are working on that. And I think STM is probably more suitable than conventional transport to actually do this.
Mm-hmm.
Thank you for the interesting talk. I have a short question. Is it possible maybe to try add small strain to the manganese telluride grown on strontium fluoride substrate, and then compare it to the gallium arsenide substrate? Maybe
Yeah,
that would shed some light on if one reason is responsible for this or another one.
Right. So I have to think about this. So it's not okay. So if I grow thin enough on strontium fluoride, which is something that we're doing, so the film that I showed you is actually 100 nanometers and 1 micron. But if we grow 20 nanometers or 15 nanometers, something thinner, then yes, the films on strontium fluoride will be strained by the lattice mismatch. Now, unfortunately, it turns out that the lattice parameter of strontium fluoride is smaller than the lattice parameter of manganese telluride, so it will strain manganese telluride in the opposite direction as gallium arsenide. So that wouldn't necessarily rule it out, and I think to really rule it out, you have to find a third substrate that has a lattice parameter that's slightly larger than manganese telluride. Maybe barium fluoride would work. So yeah, that's a good idea actually, and it's something that we're currently developing, but not on strontium fluoride because that would not be the right substrate.
Okay, I see. Thank you.
Okay, more questions? Any question on Zoom? Okay, if not, let's thank Badih again.
Thanks. Thank you.